Our next section is actually going to be section 3. We're skipping section 2. Section 2 is about plate tectonics, so I'm not really going to get into it. I'm assuming you learned that in other years. But section 3 is about acceleration. Acceleration is another fairly abstract concept that takes some thought. So if you don't quite understand this, rewatch this video a few times, or make sure you're asking questions in class. So acceleration is defined as a change in velocity. So it's built right off of velocity here. You need to realize what velocity is, and remember that is a speed and a direction. So how can if acceleration is change in velocity, then it is changing either its speed or its direction. This is kind of a misconception around other fields of acceleration, because a lot of people don't consider that change in direction as accelerating. I could be keeping the same speed going around a turn. In a physics standpoint, that is considered acceleration because I'm changing my velocity. I'm changing that direction aspect of it. In other contexts, people might not see that as acceleration, so it's very important that you understand that changing direction here is acceleration. So there are 3 ways that we can change velocity, and therefore there are 3 ways we can accelerate, and that is to speed up, to slow down, or to change direction. All of them are considered accelerating. Yes, slowing down is considered accelerating. Speeding up is accelerating, and again, changing direction is accelerating. A lot of people use the word decelerating for slowing down, but we are going to say that's a negative acceleration. So we're not really going to use the word decelerate. It's accelerate. You're either going up, speeding down, or changing direction. That comes with the formula too. Check that out. Acceleration is the change in velocity over time. So how, over this course of time, how is my velocity changing? There are a couple different ways to write this formula. So keep your variables consistent here. Acceleration is a lowercase a. That's this variable here. Change in velocity. That would be your final velocity minus your initial velocity. So final velocity would be the end result from our scenario. Initial velocity would be the beginning velocity from our scenario. And t is going to be time. So its acceleration is equal to final velocity minus initial velocity, all divided by time. Or you can use our delta symbol. Delta just means change. So this is the Greek letter delta here. Acceleration is equal to change in velocity, and change is a subtraction problem, divided by change in time. A lot of times we don't think of the change in time as a subtraction problem because you're probably starting off at 0 time. But sometimes you might be starting off, hey, we're going to start at 2 seconds into this and end at 5 seconds into this. How much time passed? Well, that's 3 seconds. 5 minus 2 is 3. Because we can have a slower velocity at the end than at the beginning. So I could start off going 50 kilometers per hour and end up stopping at 0. That would be slowing down. I can get a negative number here, and therefore I can have negative acceleration. Speed, really you didn't get negative speed. It is changing distance over time. You're either going down, you're getting closer, or you're getting further away, but distance is never really negative. So velocity tends to always be positive numbers, while acceleration can be both negative and positive. So here's an example. As a roller coaster cart starts down a slope, its speed is 4 meters per second. But 3 seconds later at the bottom of the slope, its speed is 22 meters per second, and I want to know what the average acceleration of the car is. What we can do is we can start picking out what our variables are. Acceleration, I don't really know because that's what it's asking me to find out right here. What is the average acceleration? My final velocity at the end of all of this, what is my final velocity here? Well, let's read real carefully here. As the roller coaster car starts down a slope, its speed is 4 meters per second. But 3 seconds later, at the bottom of the slope, it's 22 meters per second. That 22 meters per second here, this here is my final velocity, which is 22 meters per second. Let's not lose my units here, because that's going to be important later on. My initial velocity is the velocity at the start. That's over here. This is my initial velocity. Again, let's not lose my units. I should take note that, hey, this is nice because my units are both meters per second. I like that. I don't have to do any conversions here. Eventually we will get into conversions and some dimensional analysis, but right now we're going to keep things fairly simple. I also need a time, because remember, I guess I should bring over that equation. Acceleration equals final velocity minus initial velocity all over time. So my time here is my 3 seconds. Here's my time. And I should note, hey, that's in seconds. That's good because this velocity has a seconds portion to it. This velocity has a second portion to it, and that has a seconds portion. So my units are going to be nice. So now I'm just going to come over here to my formula. I'm going to plug things in. Final velocity, acceleration, I don't know, so I'm going to leave that as A. Final velocity is 22. Initial velocity is 4. All divided by time, which is 3. So solving my numerator, 22 minus 4 should be giving you 18. 18 divided by 3, which is my time, should be giving you 6. So my acceleration is going to be equal to 6. But what are my units for acceleration? Well, let's look at this section right here. 18 was meters per second, and 3 was seconds. So 6 would be meters per second divided by seconds. And that's kind of a strange thing to look at. But it is acceptable to leave it like that. So that is meters per second per second. I know it's kind of weird to say, but that is the unit. Or if we're good at our fraction work, right, meters per second, when I divide with fractions, I multiply by the reciprocal. So I have meters per second divided by seconds over 1, right? That's the actual thing. If I multiply by the reciprocal, I get meters per second times 1 over seconds. And that's going to equal meters on top and seconds squared on the bottom. So my units is actually going to be meters per second squared. This here is your acceleration. Please take note of the unit. Again, if you don't know how to do that, you can rewatch the video and all that. But this here is your work. So make sure I answered the question. Was the average acceleration of the car? Well, the average acceleration of the car is 6 meters per second squared. You will get tons of practice on doing math coming up. But there is your first example.